Hi all, let's take a look at the remainder of the problems in Achieve section 3.8. Number 15 had us look at the inverse cosine function. And I need you to remember that the derivative of the inverse cosine of x, just like we talked about in our notes, is -1 over the square root of 1 minus x squared. Well, this is 3 times the inverse cosine of 5x. All right, I still use that formula. I can say, well, I know the 3 is just going to get carried along with it. Technically, it's the product rule. I would say derivative of the first is 0 times the second, but that's 0 there. And then you just say plus the first now times the derivative of the second. In the derivative of that inverse cosine, it's -1 over the square root of 1 minus whatever's inside of the inverse cosine quantity squared, times the derivative of what's inside the inverse cosine function thanks to the chain rule. And of course, the derivative of 5x is 5. So this is easy to simplify, and you could just say, well, this 3, -1, and 5 will multiply to give me -15. And then my denominator will be that square root of 1 minus 25x squared. Now, in my problem, they asked me to evaluate the derivative at 1 over 8. Okay. So if I plug a 1 over 8 in for x there, I know 1 over 8 squared is going to be 1 over 64. So you'll see in my next step, I just wrote this as 25 over 64. And I chose to simplify that. You wouldn't have to. But what I did is I went to the inside and I said, well, this is 64 over 64 minus 25 over 64, which gives me the square root of 39 over 64. And then at that point, I can say, well, if I'm dividing by a fraction, then I'm multiplying by the reciprocal of that fraction. I know that the square root of 64 is 8. I'll multiply the numerator by 8. -15 times 8 is -120. I divided by that by the root of 39 for my final answer. And again, remember, there is no need to rationalize. That's a perfectly fine format for your final answer. So that was the answer I got to. For the next one, similar. Remember, the derivative of the inverse cosine is just the negative of the derivative of the inverse sine. So this problem is essentially the same problem, except I don't have to evaluate it at a certain value of x. So over here, the derivative of 3 inverse sine of 9x is the first times the derivative of the second. Derivative inverse sine of 9x is going to be 1 over the square root of 1 minus the group 9x quantity squared, times the derivative of what was inside, which is our 9. And then I can say, well, okay, at that point, I know that I can simplify and say, well, the 9 times the 3 is going to give me the 27. So I'll have 27 over the square root of 1 minus 81x squared. Final answer in that one, because like I was saying, they don't expect us to evaluate that one at any given value of x. Now, moving on down through here, 17, yet another inverse cosine function that we're asked to take the derivative. So no problem. We say, all right, again, it's the product rule. So you're going to end up with derivative of the first times the second plus the first, which is 2, now times the derivative of the second. Derivative inverse cosine of anything is going to be -1 over the square root of 1 minus whatever's on the inside of it squared. Now the chain rule says, yeah, okay, that's your derivative inverse cosine, but you need to worry about the derivative of the function that's on the inside of that. So we have to say, well, times the derivative of x to the 7th. That's where my 7x to the 6th came from. Now, upon simplifying, you'll have -2 times 7x to the 6th gives me -14x to the 6th in that numerator. And you'll see I simplified out that square root to be the root of 1 minus x to the 14th. Please do remember, power to power, you multiply. A lot of students have a bad habit and wanting to call that like x to the 9th. That would be bad, very bad. Up next, inverse tangent function. So I think off the top of my head, oh, derivative of the inverse tangent of x is 1 over 1 plus x squared. So what's the derivative of the inverse tangent of any angle? Well, it's going to be 1 over 1 plus whatever's inside the inverse tangent quantity squared times the derivative of what's inside of it due to the chain rule. Now, unlike the preceding problems that had a constant in front of the inverse trig function, this one has a function of x in front of it. So just like these, I'm really thinking, well, it's the product rule. But unlike 15, 16, and 17, that first term's not 0. So I can say, okay, take the derivative of the first, 42x to the 6th, boom, times the second, plus the first, 6x to the 7th, now times the derivative of the second, and that derivative of the second gives me 1 over 1 plus whatever's on the inside of it squared, times the derivative of what's on the inside of it. So now that I've got to that point, I can go in and say, well, all right, the 6 times the 6x to the 7th, that's going to give me 36x to the 7th. And this denominator is going to be 1 plus 36x squared. I didn't even change the first term because there's nothing we can do there. Now, amongst these two terms, I could have factored this answer. I just chose to leave it in this format, and Achieve left it, or sorry, Achieve accepted it, no problem whatsoever. Now, for one like 19, what makes it interesting? Well, I like 18 because it forces you to use the product rule. You have a first function and the second function. This one doesn't do that, but it still at least has, this is a 3-term, or I should say a 3-layer chain rule problem, because I have a differentiable function of x inside of a differentiable function of x inside of a differentiable function of x. So it's a 3-layer chain. That's pretty cool. So I can say, all right, I know that the derivative, the inverse sine, is going to give me 1 over the square root of 1 minus whatever's inside of it, quantity squared. So you can see that's why I have the 1 over the square root of 1 minus e to the 3x quantity squared. Now, times the derivative of what's on the inside of it. But we know the derivative of any exponential function is that exponential function. So that's why I have times e to the 3x. That's the second layer of the chain. But then you should have been saying, well, but John, you have a function inside of that exponential function. Yes, I have to multiply by the derivative of 3x, which is where that 3 comes from. Now, when I try to simplify this, I can say, well, 3 times 6 is going to give me 18. I'll have 18 e to the 3x power divided by this square root of 1 minus e to the 6x power. Final answer, great problem. Now, if you're thinking, well, hey, I want to do some with the inverse secant and inverse cosecant, no problem. Remember, the inverse secant has a derivative, the inverse secant of x has a derivative of 1 over the absolute value of x on the square root of x squared minus 1. Well, the inverse cosecant, it's just negative 1 over the absolute value of x on the square root of x squared minus 1. Well, what happens if you have a problem like this where it's not just x? No big deal. You just say whatever's in the argument of the inverse cosecant takes the place of x in that derivative formula. So when I take the derivative of this problem, we can say, well, the 7, that's the first, times the derivative of the second, and that's my inverse cosecant. Negative 1 over the absolute value of x to the negative 7th. And then I have the square root of x to the negative 7th squared minus 1. All of that multiplied by the derivative of what was inside of this inverse cosecant, which of course is negative 7 x to the negative 8th. Okay, at this point, I just wanted to simplify some. Here's the simplification process that I did. I took the 7 times the negative 1 times this negative 7. I can say, well, that's going to give me a positive 49. Then what I did is I said, well, if I'm multiplying by x to the negative 8, that's the same thing as multiplying by an x to the positive 8 in the denominator. So I said, well, x to the positive 8 times x to the negative 7, that's where that x to the first came from. So please understand this x to the negative 8 up here made an x to the positive 8 in the denominator. It added to this exponent and gave me x to the first. Now, that still has to be a positive term there, so I went ahead and kept an absolute value on it. Then I have my square root of, this would give me negative 7 times 2, x to the negative 14th minus 1. Now, here's what I did. I could have left it in this format. I chose not to. So Is that a correct answer right here? Sure it is, but it's an ugly looking answer. But I think achieve would count it correct. I don't like that negative exponent within the square root. So I thought about that and I said, well, what's the true power on that? You know that the square root of x to the 14th would be x to the 7th. Well, the square root of x to the negative 14th would be x to the negative 7th. I need to multiply by an x to the 7th to get rid of that. I'm already multiplying by an understood x to the 1st, so I need to multiply by an additional factor of x to the 6th. If I multiply the denominator by x to the 6th, obviously I also have to multiply the numerator by x to the 6th. So that's where this 49x to the 6th came from. Now in the denominator, I'm multiplying by x, I'm multiplying by x to the 6th. Those two combine to give me a multiplication factor of x to the 7th. Whenever you multiply by x to the 7th, you need to understand if you're putting it inside the square root, it's going to become x to the 14th. And please make sure you get this. If you took the square root of x to the 14th, it's going to give you back your x to the 7th here. And you say, okay, well, does that help? Oh, you bet it helps, because now I can distribute that x to the 14th through this expression, and it's going to give me the square root of 1 minus x to the 14th inside there. And actually, I was saying achieve might accept this answer up here, but notice in red, I said achieve requires getting rid of the negative exponent in the radical. I actually forgot. I believe I tried to put this answer in, and it didn't like that answer. It is correct. It's just not in the format that they wanted. They wanted this nicer format. So I think it's kind of cool that they required that for that problem. Up next, looking at number 21, we have an inverse cosine of 8x divided by the inverse sine of 8x. Please don't be the student that says, well, is that the inverse tangent of 8x? No, it is not. It does not work that way. So, the inverse cotangent. While cosine over sine is cotangent, inverse cosine divided by inverse sine is not inverse cotangent. So I just need to leave it the way it is, try to take the derivative. I square the denominator since it's a quotient. I bring that denominator up to the numerator times the derivative of the numerator, which I know is going to be -1 over the square root of 1 minus whatever's inside of this function, quantity squared. Well, 8x quantity squared gave me the 64x squared there. Then I said times the derivative of what was inside. That's where the 8 came from. So this is your denominator times the derivative of the numerator minus the numerator, now times the derivative of the denominator. But you know that that's essentially the same thing. The only difference is, since this is an inverse sine, its derivative is going to be +1 over the root of 1 minus 64x squared times 8. Then at that point, I just simplified a little bit. I saw that I had 2 terms in my numerator. All of this is one term, all of this is one term. Both of those terms were divided by the square root of 1 minus 64x squared. So I just thought about it as, well, I'm going to multiply my numerator and denominator by that square root. In the numerator, it's going to cancel out that term. In the denominator, it multiplies the existing inverse sine of the group 8x quantity squared. So I move this square root down to the denominator by multiplying the numerator and denominator by it. Now, when I do that, though, what I'm left with, I would have and it looks like I flipped the signs here, it doesn't really matter. What I'm left with, I'll have an 8 times an inverse cosine being subtracted. So I say I'll have -8. Oh, they're actually both negative. Yeah. So -8 inverse cosine of 8x. And then I put plus because this is all inside of a group being multiplied by -8. So notice here, this term was also multiplied by -8. So I would have -8 inverse sine of 8x. If I factor out that -8 from both terms, I'm just left with your inverse cosine of 8x plus your inverse sine of 8x. And the order of that addition, of course, is completely irrelevant. Final answer there. And I really wouldn't try to go any further. For number 22, we had a nice relation given in terms of x and y. And it's asking me the question, at what ordered pair is there going to be horizontal tangents other than when x is 0. Okay, so I went through and took the derivative with respect to x. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared dy dx. On my right-hand side, derivative of 2x is 2 times the secant y plus 2x times the derivative of the secant, which is where I get my dy dx. Now I bring my 2 dy dx terms over to the left and I factor the dy dx out of those terms. You can see I have 3y squared minus 2x multiplying the dy dx. On the right-hand side, I'm going to have 2y, and it's going to be minus 3x squared. So now dy dx times this group is equal to this group. So for my final answer, dy dx is going to equal what I have on the right-hand side divided by 3y squared minus 2x. Now, I need to know when this derivative is equal to 0, because that's going to be when it has horizontal tangents. So that's at least easy to at least think about when it's equal to 0. A fraction can only equal 0 if the numerator can equal 0. So I just take the numerator of that expression, set it equal to 0. When I do that, I solve for y. The 3x squared would move to the right, become positive. Then you would divide by 2. So I can say, well, I'm going to have a horizontal tangent anytime y is equal to 3 times the x component squared divided by 2. So in order to find out the instances where that could happen, all I do is I substitute this into your original equation up here. I know what y needs to equal in terms of x in order for this scenario to happen. So I'll say, okay, x cubed plus y cubed becomes 3x squared over 2 cubed is equal to 2xy. Well, 2x times y, which we know what y has to be, the 3 over 2x squared. Now I need to simplify. So I'll say, okay, this second term is what I need to worry about. I know 3 to the third power is 27, 2 to the third power is 8. X squared raised to the third, please remember, power to power you multiply, you'll get x to the 6th. On the right-hand side, the 2 and the 3 over 2 just multiply to give me 3, and again, I'll have x cubed. So now what I did is I just got all of the terms of x on the same side. So I subtracted 3x squared on both sides. I already had 27 over 8x to the 6th. Then I would have plus 1x cubed minus 3x cubed for a total of minus 2x cubed over there. At that point, I can factor my left-hand side. You can factor out the greatest common factor of x cubed. When you do that, you'll still have 27 over 8x cubed minus 2 left over. Now, I know the zero product property tells me that the solutions to this are when the first term is equal to 0 or when the second term is equal to 0. Well, the first term it's setting equal to 0 already gives me the solution that I know they're not interested in. They don't want when x is 0. So even though that's a valid solution, it's not the one that they want. So now I have to set my other equation equal to 0, which means 27 over 8x cubed has to equal 2. And then I can say, well, all right, then x cubed is going to equal 2 times 8 over 27. That's where I got the 16 over 27. At that point, I can say, well, all right, I need to take the cube root of both sides. 16 is not a number that has a nice cube root, so I just took the cube root of 16. But 27 is. We know 3 cubed is 27, so the cube root of 27 is 3. So I know the value for x, and I went ahead and simplified this. You could have left it like this, but I went ahead and simplified, and I said, well, even though 16 doesn't have a cube root, 8 does. The cube root of 8 is 2. So I can call the cube root of 16 the cube root of 8 times the cube root of 2, and then simplify that to 2 on the cube root of 2. So now this is my x component. And I brought that over here because I ran out of room here. I said, so the x component is 2 on the cube root of 2 over 3. Well, then what's the y? We know that the y value has to be 3 times the x component squared divided by 2. That's precisely what I did. I said, well, that's the same thing as 3 over 2 times the x component squared. So I just squared this value right here. And when I thought about that, I could say, well, all right, If this 3 in the denominator is going to be squared, we know one of those 3's is going to cancel out this 3 in the numerator. And then I'm just going to have one term of 3 in the denominator. Similarly, I'm going to have two factors of 2 in the numerator. One of those cancels with this denominator of 2. So you'd say, okay, you'll have one factor of 2 left in the numerator. And then the cube root of 2 squared, that's like the cube root of 2 times the cube root of 2, which is going to give me the cube root of 4. Still not a number I can take the cube root of. But that would be my y value. I'd go ahead and put that into a coordinate ordered pair. Final answer. And Achieve loved the format of this answer right here. They do want exact form, so don't be one of those that tries to give a wimpy decimal approximation, because they're not going to take it. Looking at the next page here. For 23, again, it's just asking me to take the derivative, but this time, not only the first derivative, but the second derivative, so higher order derivatives. That's kind of fun. So whenever I'm doing that in this problem, I can say, well, all right, I'll go ahead and take the derivative of my original relation. And when I do that, I'll remember that we're taking the derivative with respect to x. So this is going to be 9y to the 8th times whatever the derivative of y is, which is dy dx. Now, minus the 2 comes down, I'll just have minus 9x to the first, technically times dx dx, which is just a 1. On the right-hand side, derivative of any constant is 0. Now I get to this point and I can say, well, the notation they're using is y prime. Of course, that's the same thing as dy dx. So I just need to solve for dy dx. I would move the 9x to the right, it becomes positive. Then I would divide it by 9y to the 8th. That's where this came from. And then I can say, well, the 9's cancel out, and I'll be left with x over y to the 8th. Now, my second derivative. Once you have your first derivative explicitly solved for, the second derivative falls into place. You just say, well, the derivative of the first derivative is the second derivative. So I have a quotient. I use the quotient rule. Squared the denominator. Bring the denominator up to the numerator. Times the derivative of the numerator. And whenever you're doing that, you need to be thinking, okay, it's the derivative of x with respect to x. Well, dx over dx is 1. So low d high minus high x d low. Derivative of y to the 8th is going to be 8 times y to the 7th times whatever the derivative of y with respect to x is. But now, and I intentionally said whatever the derivative of y with respect to x is, but we know what it is. Now, is this a correct second derivative? It is. But what's the problem with it? We don't want to define the second derivative in terms of the first derivative unless we just have to, and we don't have to. So in this step, I said, well, I know what dy dx is, so instead of just plugging that in there, replace it with what we know dy dx is. That's what I've done here. But now, what's the problem with that answer? Well, this answer, it's a sloppy compound fraction. And please do notice I did go ahead and square out the denominator, give me the y to the 16th. And I simplified this term out to be minus 8x y to the 7th, and my dy dx is x over y to the 8th. Now, I don't want to divide by that y to the 8th in this term in the numerator. It's sloppy to have fractions inside of a fraction. I can already see I'm multiplying it by y to the 7th. That's going to get rid of most of it. That's why you see I've multiplied by a y in the numerator and a y in the denominator here. I only needed one more additional factor of y to cancel out this y to the 8th. So I can say, okay, y times y to the 7th is y to the 8th. That's going to cancel out that y to the 8th. And my second term is just going to be minus 8x to the 2nd there. That's where that came from. But that y also distributed to the first term to give me the y to the 9th minus 8x squared. And then in my denominator, we have our y to the 17th power. Pretty cool question. Last one on there, and boy, is it ever anticlimactic. Now, I say it's anticlimactic, but it's actually leading us somewhere. In section 310, we'll be doing related rates, which will be application problems, which are problems with rates of change that are all with respect to time. So Everything in that section is going to change with respect to time. It might be the change in volume over time. It might be the change in the radius over time. It might be the change in a horizontal position over time, the change in a vertical position over time, the change of an angle, d theta dt. So all of the variables in that section are functions with respect to time. So whenever you take their derivative with respect to t, you can't just simply say they're zero. That's what this problem is trying to get you used to. So I believe it said in the directions on Achieve that assume that both x and y are functions of t, which means, again, their derivatives with respect to t are not simply zero. And then you're supposed to take the derivative. Well, all right, no problem. It's a very basic equation. If I have 5xy equals 4, then you just say, well, you've got two variables. Both of these are variables with respect to time. So how would I take the derivative of 5x? You'd say, well, normally now this is where students get confused because they're like, I thought the derivative of 5x was 5. That's the derivative if you're taking the derivative with respect to x. But if you're taking the derivative with respect to t, you just say, well, that one's going to come down in front, then you get x to the 0 times the derivative of the inside. Ooh, the derivative, that's going to be dx dt. So the derivative of 5x is 5 dx dt times the second. So this is derivative of the first times the second plus the first. Now, what's the derivative of y with respect to t? I don't know, but I do know I can represent it with dy dt, derivative of y with respect to t. Now, on the right-hand side, derivative of any constant, no matter what you're taking the derivative with respect to, is 0. So now I can say, okay, in the expression they asked me to solve for dy dt, no problem. I move the 5 dx dt y over to the right side. When I do, it becomes negative. That's why I put minus or negative 5y dx dt on the right. And then you divide that by the coefficient of dy dt, which was where your 5x came into play. At that point, I eliminated the 5s. I could have kept the dx dt up in the numerator. I kind of thought it looked better out beside of it. Either way, though, it's correct. My final answer, negative y over x times the derivative of x with respect to time. Final answer, guys. All right, so that's the end of the 3.8. Please let me know if you have any questions. I had fun working this section, and hopefully you will too.